All right, so I guess let's get started, right? So welcome to this session, right? So here is the network security session, and I'm very happy to be your session chair. My name is CU from the Chinese University of Hong Kong. So in this session, we have 4 amazing papers from very different topics, right? Including how to do defenses, how to do attack, right? So this would be a fun session. Hopefully, you guys would enjoy it. All right, so for the first paper, we have Fatame from UCLA to tell us about a new hybrid attestation scheme. So Fatame, please.
Hello, everyone. My name is Fatame. I'm a first-year PhD student at UCLA, and I'm going to present our paper, IDA, which is a hybrid attestation with support for interrupts and TOCTOU attacks. My co-authors are Justin and Nader. All of us are from Secure System and Architecture Lab at UCLA. So I'm going to start my talk with embedded devices. As all of us know, there are too many embedded devices around, and they have a wide range of applications and interactions. So that makes them vulnerable to different types of attacks. So we have to ensure the integrity and security of these type of devices. For low-end devices, it's even more challenging because they have some limitations like hardware or power constraint. So a very good solution and a well-established solution in this area is remote attestation. With remote attestation, we can make sure that the program on the memory of these type of devices is not modified. So in high-end devices where we have the hardware support, it's easier because we can do the remote attestation with the help of trusted execution environments. But for low-end devices, it's harder because we don't have such a support. In the attestation process in general, we send a challenge from the verifier side to the prover, and the prover sends back the response to the verifier after going through the attestation process. And the verifier verifies whether the response of the attestation is as expected or not. We have different types of attestations, and there's a wide range of works in the academia on the attestations. They are either on software, hardware, or hybrid. The problem with software attestation is that we rely on request to response time, and this time should be less than a threshold. This is a strict assumption because it makes the device vulnerable to low latency attacks or network limitations. Although software attestation doesn't have that much overhead because we don't need to modify the hardware, and it's flexible because it can be implemented on already existing devices, it's not robust enough because we are bounded to that limited time. So the hybrid attestation is proposed to solve this issue. In the hybrid attestation, the verifier sends a challenge to the prover, and after prover gets the challenge, it goes through the entire memory. It gets its secret key from the memory and goes through the entire memory and calculates the hash. And after doing this process for all the memory content, it sends back the response to the verifier, and verifier checks whether the result of the attestation is successful or not. This is great, but the problem is that for each of the hash computations, we need to get access to the key on the memory. That secure key storage is a limitation for hybrid attestations, because we have to tame, track, and sanitize all the key-related operations each time. So we don't have the support for interrupts or direct memory access requests. Although hybrid attestation is robust and has the robustness that we were missing in the software attestation, the necessity to protect code and cryptographic key doesn't allow us to have interrupts or DMA requests. And besides that, all the attestations have the problem of time of check to time of use attack. So what is TOCTOU? In the static remote attestations, we have no information about prover before or after the consecutive remote attestations. So this makes us vulnerable to TOCTOU attacks because the adversary might modify the memory after remote attestation or hide its malware during the attestation or even erase itself before the next attestation. So in all the scenarios, when the user is actually using the device, it's compromised, but the result of the attestation was successful. So that gives us the motivation to propose IDA. IDA is a hybrid remote attestation that tries to bring the flexibility of software-based methods with the security of hybrid-based methods. In IDA, the key idea is not storing the key, because that allows us to have interrupts and DMA requests. IDA has two main components. The first one is a hybrid monitored hash computation, where we need no key to do the entire attestation process. We just make sure that the execution of attestation is correct, and we don't need any key storage for this part. We only securely compute the hash. Second part of IDA is the authentication, where we authenticate the response of the attestation through computing the HMAC. That guarantees the authenticity and correctness of the response. That's the only part we need the key. Most of the attestation problems or protocols are vulnerable to two main types of attacks. The first one is collision attack, where the adversary might find another nonce or compute the hash over another part of the memory instead of the entire memory, or finds another hash which can forge the response. But since we are using unique nonces on each of the attestations, and we are computing the hash securely, but by a secure hash algorithm, we are sure that IDA is not vulnerable to this type of attack. The second type of attack is substitution attack, where the adversary might change the memory or registers or even modify the CPU signals. But since we reside the attestation code on the read-only memory, and we are sure that the implementation is correct, and we are using a secure hash, we are sure that IDA is not vulnerable to this type of attack as well. So we figure out there are two rooms to improve IDA. The first one is the reset overhead. In the IDA, when an interrupt happens during the attestation, we reset the entire process. But we figure out all of these resets are not necessary. So we try to minimize the number of resets because of the overhead. And the second thing we improved about IDA is supporting TOCTOU attacks. So we introduced IDA Plus, which is the improved version of IDA and has two main contributions. The first one is handling interrupts efficiently. How IDA Plus does it? IDA Plus tracks all the changes to the program memory during the interrupt handling. So if the memory has not changed, we don't need to reset the process. Besides that, we save all the critical values before the interrupt, in this critical values of the attestation before the interrupt happens. The second contribution of IDA Plus is mitigation against TOCTOU problem. In this one, again, we monitor the changes on the hardware memory to make sure that when the device is used, the program memory has not modified. There are so many properties in the related work that IDA doesn't need to have them. For example, there are many works that need atomic execution, but we don't need IDA to do any atomic execution, or we don't need any DMA monitoring. We are monitoring the writes, but not addresses of the memory. But at the same time, to guarantee the security, we have some other properties that we expect from the system. For example, we have to make sure that the hash computation is implemented correctly or the system is implemented correctly. And also in the IDA, not IDA Plus, we have to reset the program after each interrupt request. I'm going to talk briefly about the architecture of IDA. We have four main parts in our system. First one is hardware module, which monitors the CPU signals and ensures security during the attestation. We have a CPU unit and memory backbone, and when we are talking about memory in our paper, we mean read-only memory, data, and program memory as well. Hardware module is the main part of IDA, and it's in charge of securely executing the software attestation. It monitors some of the CPU signals like program counter, memory address, and so on. And it has two main parts itself. The first part of hardware module is controller unit, which is a finite state machine that monitors CPU signals. And it has four main states. In the monitor state, we only monitor program counter and other CPU signals like memory addresses. And we only go to the end state if the hash computation is completed without any interruption. If interrupt happens, of course, we go to the interrupt state and so on. All the details are available in the paper, so you can check them. For the attestation algorithm, we have two main parts. The first one is the initialization, where we receive the challenge from the verifier, and we initialize our hash with the nonce in the challenge. We can also define the attestation range, but it's optional. And the second part of the attestation algorithm is computing hash over the program memory. And if the interrupt or DMA request happens during this time, we have to pause the computation and handle the interrupt, and after that, restart the computation. All this process is monitored by our hardware module, which is an FSM, and also we receive the inputs from this module as well. The second part of hardware module is authentication unit, where we validate the response of the attestation with calculating the HMAC over it. For IDA+, we said we are supporting TOCTOU attacks. How it's happening is that after last remote attestation, we have a monitor that monitors the program memory. If the program is not modified, there is no need to do anything. So the hardware module sends the response, which is the HMAC of the nonce. The nonce is part of the challenge that the verifier sends us. And if the program is modified, then we go through the attestation process and we send back the response, but the response is not valid. So the verifier can detect it and understand that the program of the prover has modified. For supporting or reducing interrupt overheads, IDA+ again monitors the memory writes, and if the memory is not modified, then we continue the process. Otherwise, we have to reset. So that's the way we eliminate unnecessary resets in IDA+. We implemented our work on OpenMSP 430 and Zinc FPGA. The implementation of IDA is open and accessible on our GitHub. For software attestation, we used SHA-256 from the Hackle library, and for hardware module, we used HMAC implementation based on SHA-256 by SecWorks. We evaluated our work by calculating the overhead in different areas, and the result was promising. IDA only adds 3% memory overhead and 90% hardware overhead in terms of the area. And most of the hardware overhead comes from the authentication part, which is calculating HMAC, and the controller only uses less than half of the overhead. IDA has almost 2 times faster attestation time compared to other hybrid attestation methods, and we only add 12% runtime overhead. In the worst case scenario where the interrupt intervals are almost equal to the attestation time, the overhead of the IDA is 2.5% in terms of energy. All the details of the implementation and evaluation are again available in the paper. So there are many works on the attestation or hybrid attestation, but a few of them are supporting TOCTOU. IDA+ and IDA are part of them. But compared to the related work, we don't have that extra storage overhead. And besides that, as we said, we eliminated the necessity of storing the key. So IDA and IDA+ are immune to vulnerabilities related to key storing. And other than that, we are able to support interrupts and DMA requests. So in order to conclude my talk, I'm going to give you a summary of what I said. We said remote attestation is a very good, promising solution to make sure that the program on the low-end devices memory has not modified. And in order to have a good remote attestation, it needs to be both flexible and secure. For flexibility, we propose not storing the key because it allows us to have interrupts and DMA requests. And for security, we need some sort of hardware monitor. And other than that, our work supports TOCTOU attacks. By support, I mean can prevent the system from these attacks. IDA and IDA Plus are our work, and it has two main parts. The first one is a hardware monitor hash computation that does the attestation process, and the second part is the authenticating the response through calculating the HMAC. IDA and IDA Plus have almost 2 times faster attestation time, and they only add 90% hardware overhead. If you have any questions, feel free to email me. You can also check our work on our website, UCLA CSARC Lab. And thank you for your attention. If you have any questions.
Thank you, Fatame, for the awesome talk. So any questions from the audience? I guess you can use the microphone on here. Questions? Yeah.
Hi, great talk. How did you measure the power consumption? You said this is done on an FPGA?
Yeah, we implemented our work on a Zinc FPGA, and we got the result from the FPGA.
Thank you.
No problem.
Any other questions from the audience? If not, then I have some questions for you. So first is I'm curious to understand the key storage part. So here you're claiming that you don't really need key storage. But then, if I understood correctly, you are still doing HMAC, right, which would require key. So I didn't quite get the, like, where is the key being sort of saved?
We are claiming that you don't need the key during the attestation process because if you wanted to store the key and get access to it, then you had to obtain and track all the key-related operations. But we do the entire attestation process, and at the end, we only calculate or compute the HMAC over the response, and it's only one time, and we send it to the verifier. So you don't need to get access to the key during the entire attestation process, so we can have interrupts or everything because we don't have taint secret data.
I see, understood. All right, so any other questions? If not, then I guess we can thank the speaker again.
Thank you.
Thank you.